fast it are more effective. So there's 4 tools that I came up with. Although I know for a fact there's more, I just threw these in there because they're what I actually use and what I find to be extremely useful. Bin Navi by Sabre Security is a way to visualize code. It's a way to, and it's highly graph-based, right? I got arrow over here. Very useful. It tries to use graphing to display all this information, and the next one is the same, PyEmu, and it's created by Pedro Mamini, who actually I work with. Both heavily use graphing to visualize these code blocks and all this code into a way that makes sense. It's done through, graphing branches or, graphing data flow and things like that. So they're very useful at paring down this massive amount of information into something that a person can actually use. It includes debugging and static analysis and scriptability and things of that nature. And the next 2, Chris Eagle, I think he spoke here a couple of years ago. He wrote a x86 emulator plugin for IDA with a GUI. You can set data and you can do all these different things, and it's really good. I know a lot of people that use it. And then, of course, PyEmu, which I like to think as the next step after IDA x86 emulator, the next step in using Python or scripting languages or in emulators and reverse engineering. So now that we've covered that, we're going to cover the PyEmu architecture and how it's all laid out and how each piece makes up the whole. So why Python? And since most of you are Python users, I'm not going to get crucified for writing an emulator in Python. Low-level code is not normally done in a high-level language. I don't know many people that would even think that was something you'd want to do. But logic is all we are trying to achieve. And since it's a utility emulator, doing logic in any scripting language, any programming language is certainly possible. Speed is not a priority. Again, being a utility emulation, we're not going to be emulating Quake or emulating, World of Warcraft, although you could try. And then, most of all, I think, is there's so many good Python reversing tools and so many things written in Python that are related to reversing, vulnerability research, exploit development. You have Canvas, and I think Core has some Python extensions. You have a lot of different third-party and, people in the community that have written libraries for it. You have PyEmu and PyDebug, which we'll cover a little bit later. But all these things are helping to allow people to integrate scripting languages and scripts into achieving these tasks. So that's one of the main reasons I chose Python. So just a quick overview. We have in PyEmu I've separated out the CPU, the memory, and the publicly exposed emulator portion. And the reason I do this is to allow more autonomous control of each subsystem. I wanted to make it easily expandable and flexible, or flexibility is the main purpose of the architecture. I wanted to allow people to just completely rip out parts and use it for themselves, or to only use the actual CPU portion of the emulator. I have my idea of how I use it. You may have a completely different one, and I like that. So wanted to make it a little bit decentralized and really flexible. Oh, here's my MS Paint of the architecture, which someone wouldn't leave me, someone from Tipping Point told me to kind of move that out a little bit. So I made a little more professional one. And, it's split along these 3 layers. You have the user scripts, and then you have these, what I call environments. And I realize that the names I've chosen for these is horrendous, but it's just to be more verbose, a little more descriptive. So when I say PyDebug, PyEmu, don't crucify me, You could change it if you want. I don't mind. But calling through these emulation, I'll call them environments. You'll hit the main PyEmu base class, and that will be responsible for exposing all the methods we're going to use, handling all the user requests, controlling execution, transferring control from the, emulation to the user, And then that talks to the bottom two, PyCPU and PyMemory, which I'm sure you can infer what they do. And we'll go over them a little more in a second. But PyCPU is the less than 3 of the emulator. Handles instruction logic, as you would assume. I based it on the Intel reference as much as I could, and kind of just, I even have the comments inside of the CPU are actually copy and pasted outside the Intel reference. So if you want to go in there and look, it's all really unrolled, and I didn't optimize any of it. It's, I don't remember, 20, 30,000 lines in the CPU, but we have computers we can search. So I did that, though, to allow people to go in and instantly read what's going on and instantly add to the CPU class. I have here I tempt autonomy as much as possible. I'm going to use autonomy lightly because it does rely on the emulator and the memory, but there's nothing in there that's stopping you from saying, and I've done it in testing, just executing raw instructions through the CPU. You can't execute an instruction that reference memory, but you can still run through some different instructions and get some use out of it. So, in essence, this is the, fetch, decode, execute that all the CPUs do. You have instruction fetching, request code section bytes from memory, decodes it via PyDASM, grabs a mnemonic, calls a handler, updates the IP. I mean, that's pretty simplified version, but it's all the CPU really does. And I will have a lot of Python examples in here. I'll skip through them pretty quick, but for those that want to squint their eyes and read it, they can try to. But it's what I basically explained. We get an EIP, fetch the code section, bytes, decode it, hand that off to our handlers that will work on that mnemonic, and then update EIP if necessary. So I wanted to take a second and talk about the selective mnemonic support in PyEmu. I only support about 120 mnemonics. And if you've ever looked at the Intel spec or the x86 instruction set, there's actually 400 plus. And I don't remember the number, but 400 instructions. As I was going into this, I looked at it and I said, there's 400 instructions. May not be worth it. I'll focus on these. And there's a reason for that. I did some statistics on the instruction set, and I ran a script I wrote in Python to basically get all the mnemonics in a binary. And it came out to only be, to be less than 100 instructions that actually get executed. And I didn't run it on, something tiny. This is kernel 32. It's fairly well known, I guess. But you'll see in here, the most used instructions get a heavier weight. They're larger and bold. Call, compare, moves, pushes, all those I certainly have support for. A lot of the obscure instructions I don't. But like I said, if you want it, you can add in about 10 seconds. I don't know how many people are familiar with the x86 instruction set, but LOL is not really a instruction. Although it's used a lot in kernel 32, I don't know why. I don't have support for that one. Maybe I should. Maybe it'll print out ASCII, something like that. Some ASCII logo. So just some convenience functions if you're ever in PyCPU and you wonder how all the different instructions actually look the same, and it's because I use these convenience functions. Get register, set register, get memory address will actually decode the SIB, the mod RM, all those things to calculate these memory addresses. And so if you're implementing instructions, you can use these easily to, make it more uniform like the rest of them are. Next we have PyMemory. Again, PyMemory handles memory requests, including the text section, the data section, all the read-only stuff, any of the memory that's actually going to be accessed inside of the emulator. You'll call through this class. And the way it works is that it'll fetch memory and it'll cache it. So anytime it needs it again, it'll be in its local cache. And I do this for several reasons. It's mainly to, ease the fetching of memory, but it's also so that at the end you could say dump out all the memory that was accessed and the contents of that memory. And for instance, in the PyDebug example, one of the ideas was that you could dump out the context from the emulator and restore that back into the actual process if you wanted to. Or you could log it, write it to disk, whatever. PyMemory, the actual class, gets overloaded or inherited, I should have said, from the environment classes. The new environments communicate with the parent, of course, to get at the cache, to store into the cache, things of that nature. And what it does is it allows us to add environments easily. You'll see that later we implement memory managers, as I'll call them, for different environments. And the environments are IDA, PyDebug, a PE file, things of that nature. If you wanted to, say, create a network emulator that listened on a port for instructions, you would create a network PyMemory class that would, know how to fetch memory, so that when the base class says, I need a page of memory, it'll call back into the inherited class or the child class, and it'll know how to fetch that, whether it's call back over the network or get it from the real process or whatnot. So, this is exactly what I said. There's get page, get and set memory and whatnot. And then you have PyEmu, which is the class that is the main interface to the user, handles initialization of the memory, the CPU, contains all the useful methods that we'll go over in a bit. And in most cases, we subclass this or inherit from this to create those environment classes that I was speaking of. As the user, you would only instantiate really the PyEmu classes. And just real quickly, we'll go into these later. These are a couple of different methods that I provide through PyEmu. You'll see handlers, modification, execute, of course. Logging, dumping, memory, stack, SEH, registers, context. So to further expand on the environment classes for the emulator, you have IDA PyEmu, PyDebug PyEmu, worst names in the world, PE PyEmu. But when you look at them, you can tell exactly what they're doing and which one you're going to instantiate. So what they do is provide a class for that environment. You wouldn't want the PyDebug memory handler to, fetch memory for IDA and whatnot, because it wouldn't know how to do that. So it's real easy to create them. It takes 10 minutes in most cases to create a new one if you need it. So it's real easy to navigate through. And you'll see this example, this is PyDebug. We'll store the debug object and then set up context and memory. And I don't have the full thing, but it's kind of a synopsis on the instantiation. So user scripts, the top part of that graph we looked at, is created using the exposed PyEmu API, allows the user to fully control emulation, allows someone to maintain control via handlers, and can be run in various situations. Like I said, you can run it on a live program or process that you're debugging. You can run it on static in IDA, and you can run it just straight from the command line using the PE file parser that I use, the Python PE file. So it gives you a lot of flexibility. It lets you create scripts that you can execute in different environments. Depending on your workflow, you may be a person that uses debuggers, you may be a person that just uses IDA, and this lets you use an emulator